the integral from 0 to half pi over 4 square root of tangent x dx. So first I'm going to tangent square root of tangent x equal to t. So tangent x is equal to t squared. Right, so therefore x must be arctangent t squared. Right? So dx has to be first 1 over t squared plus 1. Right? We treat t squared as a whole entity. Right? Therefore, we differentiate chain rule. Right? 2t. Right? Differentiate inside 2t dt. Right? That is t to the power 4 plus 1, 2t dt. Right? Of course, change the boundaries. Right? So when x is equal to 0, t is equal to 0 as well. When tangent x is equal to pi over 4, right? T must be equal to tangent pi over 4 is just 1. Square root of 1 is 1. Right? New boundaries 0 to 1. So therefore, integral this time is equal to 0 to 1. 0 to 1. Tangent x becomes t. Right? Dx becomes this one. So t times this value, right? 2t squared dt. And then over t to the power 4 plus 1. Now the inside, the integrand. Right? The integrand, see if we can, let's see if we can split it into two different fractions. Right? So that is equal to 2t squared, right? T to the power 4 plus completing the square, twice of t squared plus 1 minus twice of t squared. Right? That is equal to 2t squared t to the power of 2 plus 1, right? Square. So that's essentially t to the power of 4 plus twice of t squared plus 1, right? That's this part. Then we have to minus twice of t squared. Right? That is further equal to twice of t squared. T squared plus 1 minus difference of perfect square minus square root of 2 times t times t squared plus 1 plus square root of 2 times t. Then of course we just split it into two different fractions. And then later we're going to determine the constant. So constant at the top plus the other constant on the top. At the bottom we have two factors, t squared plus 1 minus square root of 2 times t. T squared plus 1 plus square root of 2 times t. Right? So since we want 2 times t squared appear on the top, so that means can we perhaps insert two constant at the top? So we have constant times this, constant times that. We're hoping to cancel out the constant times 1, constant times square root of t. Right? Constant times 1, constant times minus square root of t. We're hoping to cancel them out so that the only thing we can have is square term. Right? But that won't happen. Right? That won't happen by just having two constants up here, because even if we can cancel out the plus 1, it's impossible for us to cancel out the negative square root of t, square root of 2 times t, and positive, because they're all opposite signs. Right? Otherwise, even if we can cancel out this term and this term, it's impossible for us to cancel plus 1, because again they happen to be of opposite sign. Right? So it's impossible to have just only two constants at the top. So maybe we can, so generally speaking, we can just AT plus B, CT plus D, right? Then just multiply this onto this bottom, right? And multiply this by this factor. Then we can just expand everything and compare the constants, compare the coefficients. But let's just guesstimate a little bit. Perhaps I can just use t, right? Because t times t squared, t times 1 t. So I have t cubed, right? But I don't have t cubed here, so I'm hoping to cancel out the t cubed. So perhaps I can write minus t. So therefore I can have minus t times, so minus t cubed can be cancelled out. All right, so t times plus 1, right? Minus t times plus 1, right? T minus t can be cancelled out. T minus t times square root of 2 times t, minus t, right? They can just stay. So in the end, I'm looking at the numerator, right? Numerator, I finally have numerator square root of 2 times t squared, right? And plus minus t minus, so plus square root of 2 times t squared, right? Because everything else is cancelled out, right? T cubed minus t cubed, t, right? minus t cancelled out. Right? This is what I have on the numerator, and that is twice of square root of 2t squared. Compare with this numerator. Right? The only difference is square root of 2. All I have to do is to multiply by its reciprocal. Right? It's reciprocal. So I'm just gonna yes. So multiply by 1 over square root of 2. Right, this is what I have. So that's the integrand. Right. So again, I'm looking at the bottom, right? The bottom involves this. So if I just use log, right? It's antiderivative, right? Log of t squared plus 1 minus square root of 2 times t. But if it's log of this value, right, then I have to differentiate log. I differentiate log. This sits at the bottom, but then I have to use chain rule. Chain rule 2 times t. But I only have t. So maybe I can multiply by 2. Maybe I can multiply by 2. And also multiply by 2. Right? Factor out the 2, I have to divide by 2. 2 times square root of 2. Right? But that won't be enough, because when I differentiate log of the bottom, not only will I have twice of t, I also have minus square root of 2. Right? Yeah. Also, I have twice of t, right? Twice of t plus square root of 2. So I can minus twice of t plus square root of 2. Right? That won't be enough. So minus square root of 2 plus square root of 2. Right? Plus square root of 2 minus square root of 2. Right? So then I can just split them up. Right? One part antiderivative is log of the bottom. Right? The log of the bottom. Right, so this time it's 1 over 2 times square root of 2 times, like I said, 2t minus square root of 2 over t squared plus 1 minus square root of 2t plus square root of 2 over completing the square, right? T minus half of square root of 2 square. Then half of square root of 2 square. 2 over 4, that's half. Yeah, but I have plus 1 here, so I just plus half. Right. So likewise, I have minus, again, 2t plus square root of 2, t squared plus 1 plus square root of 2t. Right? Right. This antiderivative, like I said, it's already log of the bottom. I don't worry about that. So all I need to worry about is minus plus square root of 2 over completing the square. T plus half of square root of 2 square. Right? Again, plus half. Right? So half square root half of square root of 2 half plus half 1. Right? Exactly the same thing. I don't have to worry about this nor this, right? All I have to worry about this and that. But this already looks like the derivative of arctangent. Right? Of arctangent of what? Right? Perhaps I just multiply by 2 on both top and bottom, right? Multiply by 2. Right? So this will become just 1. Multiply by 2, right? And multiply by 2. This will become just 1 multiplied by 2 as well. And not only that, I can just, 2 is square root of 2 square. Right? Then I can just put the square root of 2 inside, because combine the square, right? Then put the square root of 2 inside. Right? That is, distribute square root of 2 onto both of them, right? Right, distribute square root of 2. Square root of 2 multiplied by this is just 1, right? And then the square. You can just put the square root of 2 inside, combine the square, right? Distribute the square root of 2 onto both of them, right? Square root of 2. Square root of 2. The square root of 2 distribute to the square root of 2 over 2. That is just plus 1. Plus 1. Looks like it's arctangent of this quantity. Arctangent of this quantity. Right? Then we can just multiply by some constant. Right? So everything is fine. I is 1 over 2 square root of 2 times. Right. So this antiderivative, like I said, log of t squared plus 1 minus square root of t, square root of t, 2t. Right? Like I said, when we differentiate this, we can have put this down the bottom, differentiate inside, right? Twice of t minus square root of 2, right? This is already fine. Right? Then I'm looking at this, right? This antiderivative, log of the bottom, right? T squared plus 1 plus square root of 2t. And now I'm looking at this and this. Like I said, arctangent. Right? The question is arctangent of what? Like as arctangent of this whole entity, square root of 2t minus 1. Right, multiplied by some constant. Because when I differentiate this, right, I should have this square plus 1. Right, differentiate inside, differentiate square root of 2, right? Then I have to divide by square root of 2, cancel it out, right? So divide by. Then I have to multiply by this constant, right? So divide by square root of 2, the square root of 2, gone, right? I'm only left with 2. Just twice of. Right? How about this? This same thing. For the same reason, twice of arctangent of the whole quantity, right? The whole entity. Right? Evaluated from 0 to 1. 0 to 1. Yes. Now that is 1 over 2 square root of 2 log of 1 minus 2 plus 2 minus 2 minus square root of 2. Right. The other log is 2 plus square root of 2. Right, so I'm done with log. The arctangent. Right? So arctangent is what? Arctangent square root of 2. Twice of arctangent of square root of 2 minus 1. Right? The other arctangent is twice of arctangent of square root of 2 plus 1. All right, then I have to insert 0 into it. Right, insert 0. So log 0 plus 1 minus 0, log 1. Log 1 is 0. Right, so the 0. Log 0 plus 1 is 0. Log 1 0. Gone, right, this 0. So twice of arctangent minus 1. Plus twice of arctangent of negative 1. And also, no, I should say minus. Right, minus. So again, minus twice of arctangent. 0 into it. Arctangent of 1. Now this time, the integral is in fact the 1 over twice of square root of 2 times log. I combine the logarithm 2 minus square root of 2 and over 2 plus square root of 2 at this time. Plus arctangent. First I'm going to plus. So first I'm going to deal with this. Right, so it said arctangent of negative 1. Right? Arctangent of negative 1 is just negative pi over 4. And this is just pi over 4. Right? So negative 2 times negative pi over 4 becomes positive half pi, right? Becomes positive half pi, right? And this negative, right? This negative 2 times pi over the negative half pi, right? So they're gone, right? So all I have to worry about is this. It says twice of, but then I'm going to deal with, I'm going to simplify arctangent. Right, square root of 2 minus 1 plus twice of arctangent of square root of 2 plus 1. I'm going to simplify this as well. Also simplify log as well. So first of all, log. So the log 2 minus square root of 2, 2 plus square root of 2 is simply log 2 plus square root of 2 times 2 minus square root of 2. 2 minus square root of 2 times 2 minus square root of 2, right? Same thing. That is just log of 4 minus 2, right? Totally complete square, perfect square, right? 4 plus 2 minus twice of 2 times square root of 2. 4 times square root of 2, right? That is just 2 at the bottom, right? That is just log of 6 minus 4, 6, right? 2 cancel, 2 simplify. 3 minus twice of square root of 2, right? But that's equal to log of 3 can be written as 1 plus 2. 1 plus 2, right? But 1 is 1 square. 2 is the square root of 2 squared, right? It says minus twice of square root of 2. That is perfect square. Right, perfect square. 1 plus what? That is, it says 1 minus. In fact, 1 minus square root of 2, then squared, right? Yes, so that is equal to, just take down the power, twice of log of square root of 2 minus 1, right? Making sure it's positive. So log has been simplified. Right? Now I'm dealing with arctangent. See if we can simplify that. So remember, tangent alpha plus beta is equal to tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. Right? So let's say we treat arctangent, it says square root of 2 minus 1, right? Let's just call it this alpha. Right, so that means tangent alpha, right? That's the angle, right? That's the trig value, square root of 2 minus 1. Likewise, arctangent, it says square root of 2 plus 1, right? So that is equal to angle beta. So likewise, tangent beta is square root of 2 plus 1. So according to this formula, so this time, tangent alpha plus beta, right? But tangent alpha plus tangent beta. So tangent alpha plus tangent beta, right? Over 1 minus tangent alpha times tangent beta, right? That is equal to what? That is equal to twice of square root of 2. 1 minus, right? 2 minus 1, 1. 1 minus 1, right? Is it equal to positive infinity? Right? The denominator makes no sense, right? The denominator cannot be 0, but I'm asking, could it be equal to positive infinity, right? That's my question. Because I'm talking about tangent, right? So as long as we can show tangent is positive infinity, then we can show that the angle must be half pi, right? Tangent half pi. And could it be negative infinity? Not possible. The reason is because the reason I say tangent plus beta must be positive. Right? The reason is because tangent alpha is approximately 0.4 something, right? So tangent alpha is already in between. Tangent alpha is already less than positive infinity, right? Less than, at the same time, positive. Right. Likewise, tangent beta is obviously less than positive infinity, right? So they're both positive constants, so which means alpha and beta are both in between 0 and half pi. Zero and half pi. And the unit circle. Right. Both tangent value are just some constant positive. Right. Positive constants at the same time. Yet one angle may be somewhere here, right? And also, right, this tangent alpha must be strictly less than 1. Right, so the meaning the angle has to be in between 0 and half pi. Right, 0 and half, somewhere here. Right, arctangent, right, so beta. Right, tangent beta may be somewhere here, right? Beta less than positive infinity, so maybe somewhere here, right? So the sum of those two angles, right, has to be in between half pi plus half pi. It must be in between pi and 0, right? So no way could the sum of the angle be negative half pi, right? Or 3 pi over 2, no way, right? So it must be half pi, right? That's what makes tangent angle equal to positive infinity, right? That's the only possible explanation. So that way, twice of arctangent, right? Twice of arctangent, right? Arctangent, alpha plus beta, half pi. Twice of it becomes just pi. Right? So 1 over twice of square root of 2 multiplied by log. Twice of log square root of 2 minus 1. Like I said, twice of half pi becomes pi plus pi. Perhaps that's square root of 2, 1 over square root of 2, log square root of 2 minus 1, and plus pi over 2 square root of 2